When an object falls near the surface of the Earth, it always experiences this constant acceleration of about 9.80 meters per square second towards the Earth. There's this famous experiment, you probably heard about it, where Galileo Galilei dropped two objects that had different masses towards the center of the Earth, or dropped them off the Leaning Tower of Pisa, and they both accelerated at the same rate. One would hurt more, the heavy one would hurt more if it hit you, but they both accelerate at the same rate, and that's the rate in the SI system, 9.80 meters per square second. So we can use that as A whenever we have a free falling object, an object that's not being thrown down, but is just being dropped near the surface of the Earth. Now, if it's a big fluffy object that has a lot of wind resistance, that's going to be modified a bit. But to make things simple, we're going to assume we don't have big fluffy wind resistant objects, at least for now. So here's an example problem that involves free fall. A bowling ball drops from its initial resting position at the top of a 150-foot water tower. So analyzing the problem, I'm going to draw a picture of my water tower. Here's my bowling ball. It's in a resting position, so that means VI is 0. It's at on a 150-foot tower, so that means this distance here is 150 feet, and it's going to hit the ground, it's going to fall to the ground, and I want to know what is its final velocity. How fast is it going when it hits the ground? Well, what do I know that links these things together? I know that final velocity is equal to the square root of initial velocity squared plus 2 times A times D. That's what I know. Now, I can make this a lot simpler because of two things. One, it's initially at rest, so that its initial velocity is 0. And the other thing is the acceleration is g, because this thing is in free fall due to gravity. So this equation becomes Vf is the square root of 2 times g times d. Now, g is in meters per square second. D can't be in feet. So I'm going to have to do a little unit conversion here. I'll do that right here, 150 feet. And I'm shooting for meters. Well, a foot is 12 inches. That'll be my first starting point. And an inch is 2.54 centimeters. So that'll get me into centimeters. And there are 100 centimeters in a meter. So when I do my arithmetic here, I'll have my height of my water tower in meters. Here I go, 150 times 12 times 2.54, and then I'm dividing that product by 100. So 150 feet is 45.7 meters. So that's my D, and A is G, which is 9.8 meters per square second. So I'll plug all that stuff in here to tell me that my final velocity is the square root of 2 times 9.8 meters per second squared times my distance of 45.7 meters. Let's look at the units. Meters times meters is meters squared. Meters squared divided by seconds squared, when I take the square root of it, will just be meters per second. And that's a velocity term. So now I just do a little arithmetic. 2 times 9.8 times 45.7, and then I take the square root of it. So that tells me when it hits the ground after this fall, it's going to be doing 29.9, about 30 meters per second. Here's another problem we have that's going to involve gravity. We've got a model rocket falls from the top of its trajectory to the ground below, it says. So a rocket goes up like this, and then it comes down. Now the rocket is moving in this direction too, but we're only going to look at one-dimensional motion here, just its fall. So it goes up to the top of its trajectory, and its motion in the vertical axis here is nothing at that point. Its velocity is zero at the top. So that's, as we analyze our problem, that's one of the things we know. Initial velocity as it falls downward is zero. It tells us that it takes 4.62 seconds, so that's information that we know. Delta t, that time factor that we use, is 4.62 seconds. The question is, how high was the rocket when it began its fall? So that's what we're trying to find. D, how high was it when it started its fall? And another piece of information that's built into this is that acceleration in any equation we use is going to be g, because it's accelerating due to gravity. So now we've analyzed by asking ourselves what we know and what we need to find. Let's make a plan. So here's our plan. Remember, in a plan, you're always trying to find an equation that links the stuff you know, which in this case is acceleration, initial velocity, and delta t, with what you need to find, which in this case is d. Well, one of our equations that we developed today will do that, and that is this one. D is initial velocity times delta t plus acceleration over 2 times delta t squared. So now that we have a plan, let's just plug our units in and compute. So we're at the compute stage. D is equal to initial velocity. Well, that was 0. So this whole term just disappears, which makes things simpler. So 0 plus acceleration over 2, but acceleration was g. So g over 2 times delta t squared, which is, g is 9.8 meters per square second. That's going to be divided by 2 times delta t, that's 4.62 seconds squared. Start the evaluate phase here by looking at what happens to units. When I square seconds, I also have square seconds in the denominator here, so the time term just disappears entirely. Square seconds cancel with square seconds. That leaves me only meters, and that's good because what I'm trying to find here is a distance. So now I'll just compute. I'll just take my calculator and figure out what this should be. 4.62 squared times 9.8 meters per square second, and then I'm going to divide that whole thing by 2 to get my answer. And this is telling me that my rocket fell from a height of 105 meters.